There is an extremely odd structure hidden beyond our Milky Way. It is evident that the center of repulsion is at least as strong as the attraction exerted by the Kangtai, so-called Shapley attractor. But why is our home galaxy being pushed through the universe, and what does this mean for our future journey through space? Has the dipole repeller somehow managed to outsmart gravity and reverse the law of gravitational attraction? Astronomers discovered a region in space some time ago that actually repels the surrounding structures rather than attracts them. This unusual area is still the subject of astronomical research today. Make sure you follow along until the very end to learn more about this fascinating finding. Our Milky Way is not a cosmic loner. Rather, it is an essential component of a hierarchically structured collection of galaxies and galaxy clusters. More specifically, the Milky Way is part of a massive region approximately 520 million light-years in size, which experts have long referred to as the Lania supercluster. However, a recent discovery is calling into question this classification, but more on that later. What is certain is that our home galaxy and the larger local group are not stationary in space, but rather travel at a speed of 630 kilometers per second, or 2 million kilometers per hour. When it comes to the question of the origin and direction of this movement, researchers have long pointed astronomers generally assumed that most galaxies and clusters were moving toward this gravity-rich zone. But when the team led by Yehuda Hoffman from the Hebrew University of Jerusalem arrived on the scene, they discovered that there are entirely different structures out there that significantly influence our cosmic course. This is the largest known collection of galaxies at a distance of up to 700 million light-years, and as a result, a huge center of mass in which such extreme gravitational forces are at work that no increase in distance between the galaxies due to general cosmic expansion can be observed within its sphere of influence. In order to determine how the experts found the dipole repeller, they used images from multiple telescopes, including the Hubble Space Telescope, to track the movements of galaxies in our supercluster. Using this information, they developed a MELA, higher-level flow field for our cosmic environment, a model that meticulously maps the speeds and lines of motion of the structures it contains. However, this ultimately revealed something that nobody had anticipated. The galaxy's lines of motion were not all moving in the direction of the Shapley attractor. Rather, on the other side of the Lania region, experts have found a remarkable clustering of lines that deviates sharply from the typical pattern but exhibits repulsion rather than attraction. Hoffman remarked, "We discovered that our Milky Way is eclipsing a sizable, hitherto undiscovered area of low density in space, and what this low density implies becomes evident when we take into account the following. The intriguing thing about this is that the experts' calculations revealed that the dipole repeller influences our local group's movement almost as strongly as the Shapley attractor's attraction. Both zones contribute roughly the same amount to the local group's speed." The researchers stressed that this was the first time that such a source of repulsion had ever been identified in space. What does the term repulsion actually mean in practical terms? Does the dipole repeller actually repel in the truest sense of the word? Are anti-gravitational forces at play here? Well, not exactly, but first things first. Primarily, two forces operate in the universe: gravity and dark energy. On a larger scale, however, only gravity matters to us because we know that it is the force that attracts masses to other masses. Or, to put it another way, stars attract planets and other stars. The principle that gravity always attracts applies in classical physics, regardless of the specifics of the constellation. There is no such thing as repulsive gravity, so how come the dipole repeller literally pushes us away or is called the center of repulsion? In this case, the key factor is not what the region does, but rather what it does not do. Because of its low density, it does not attract us because it contains very little mass, which is precisely why it appears as though we are being repelled from it. The Shapley attractor is located on the opposite side, and this is the only reason why this is the case. There is an extremely large amount of mass that has a strong gravitational pull on us, however, since there is no comparable gravitational pull on the opposite side, an imbalance arises, and it's precisely in this imbalance that we move away from the empty side and toward the side with more mass. To illustrate this better, we can imagine the universe as a large elastic rubber mat. If we place heavy balls on this mat, they create depressions that represent massive regions that exert gravity. However, as soon as we place a smaller ball, such as our Milky Way, on the mat, it will roll toward the depression that is toward where the mass is. If we don't place anything on the other side of the mat, no indentation is created there, meaning there is no gravity to hold the ball in place. It therefore rolls away from this empty spot, even though it has not been actively pushed away. It is simply not attracted, and that is enough to create a movement away from the void. And if we now return from our rubber mat to the vast expanses of space, we see that the overall flow pattern away from the void in the measurements only looks as if something is pushing. Astronomers have therefore called this area a repeller to choose an image that describes the observed behavior in reality. However, the dipole repeller does not repel anything at all, but merely does not attract anything. And that is a crucial difference. Despite all of this, this discovery is still very important because it demonstrates that mass absence also plays a significant role in galaxy movement. Accordingly, our Milky Way is moving away from empty regions and toward massive ones. The motion of our local galaxy group is therefore caused by two opposing forces, a massive attractor on one side and an empty region on the other, from which we are colloquially falling out. This combination creates a movement pattern that resembles a dipole with a positive pole of attraction and a negative pole of apparent repulsion. Apart from that, there is also the fundamental question of where our journey through space is actually taking us, and what megastructure represents our true cosmic home, as briefly mentioned. As part of the Cosmic Flows 4 project, a research team led by Aurelian Valad from the Leibniz Institute for Astrophysics in Poten has studied the movements of over 56,000 galaxies, challenging the long-held belief held by previous researchers that our galaxy group is a member of the Lanius supercluster, which is made up of about 100,000 galaxies. However, the scientists found that the previous picture of the Lanius supercluster may not be accurate. Instead, they found 17 so-called basins of attraction, gravitational catchment areas, in which galaxies converge due to the gravity of large masses. The analysis's goal was to better understand the universe's large-scale structure, specifically how galaxies move in space and which regions they gravitationally attract. One of these basins is the Sloan Great Wall, a massive galaxy cluster and one of the biggest structures in the entire universe. In fact, its area of influence is more than twice as big as the Shapley superclusters. And what's most fascinating is how our Milky Way's movements take place inside these structures. According to the study, about 58% of the galactic currents associated with our home galaxy flow towards Shapley and only about 40% towards Ionia. This suggests that the Shapley attractor may have an even greater influence on our galaxy than previously believed, and that we may not truly belong to Ionia after all. However, this unexpected discovery inevitably raises important questions. Do we need to redraw the borders of superclusters entirely, and have we misdiagnosed our galactic home? This is not just a change on the cosmic map. It's a significant advancement in our understanding of the dynamic gravitational landscape of the universe. The study, which was published in the journal Nature Astronomy, suggests that our previous classification was too simplistic and needs to be significantly revised in light of new data. It demonstrates how complex the interaction between massive galaxy streams is and how strongly we are influenced by invisible mass distributions that extend over hundreds of millions of light years. If you click the subscribe button now, you'll never miss a new video from us again. We'd love to have you join our community so you can stay up to date going forward. See you soon.